What is liquid smoke?
It's actually exactly what it sounds like, as crazy as that is. Smoke from a wood-burning fire is blown into condensers, which collect many of the volatile chemicals in smoke. This mixture is then diluted with water. It's used to cure bacon and flavor many other foods.
Why do hard-boiled egg yolks turn green?
When egg whites cook, a small amount of hydrogen sulfide, H2S, is released from sulfur-containing amino acids like cysteine or methionine. If the H2S migrates to the yolk, it combines with iron atoms to produce ferrous sulfide. FeS, which is a dark-colored material that looks green mixed with the bright yellow yolk. Ferric sulfide, Fe2S3, is also sometimes claimed to be formed in this process. Likely because it is itself a yellow-green substance. There is, however, less data to back this up, aside from the convenient color match.
Why do shrimp change color when they're cooked?
Some, but not all shrimp, are grayish when they are raw, but turn pink once they're cooked. It makes sense to guess that this is because some chemical compound with a red color is being produced once you add heat. What's actually happening, though, is that the more intense pigments in the shrimp's shell are decomposing with heat, while the compound responsible for the red color is more stable. That red molecule is called astaxanthin. And it's not only found in shrimp shells but is also the reason that salmon meat is red. You'll probably be interested to know that there are a good number of chemistry experiments that you can perform right in your own home. While we can't teach every principle in this book with experiments that you can do with household items, we will do our best to illustrate some of the basic principles. Mostly those relevant to basic chemistry lab work, with items you may already have in your kitchen.
Why would anyone add carbon monoxide to tuna?
Cutting a tuna fish exposes many muscle cells to oxygen, which slowly changes the bright red color of fresh tuna steaks to a darker brown. This is the result of iron-containing enzymes, myoglobin and hemoglobin, being oxidized from Fe2 to Fe3. Sushi lovers have come to understand that fresh raw tuna should be bright red and are skeptical of eating any brown-colored fish. The seafood industry figured out at some point that adding Co during the packaging step not only slows the rate of oxidation down, which increases shelf life, but also brightens the red color. It does this because Co binds more strongly to the Fe2 center than Fe3. The risk to consumers is not co-exposure here, but that you might be fooled into eating fish that isn't as fresh as you might otherwise think if you judge its freshness based on color.
How can I make a lava lamp at home?
Note, okay, so we'll disclose up front that this experiment won't actually make a lamp. It will make a device with bubbles that rise and fall just like a lava lamp. But you'll need a flashlight or other light source if you want it to be illuminated. Chemistry principles encountered in this experiment: chemical reactions, density, miscibility, gases, materials you'll need. Vegetable oil, 20 ounces. Plastic soda bottle, 20 ounces or 1 liter, water, 1 tablespoon. Alka-Seltzer, R, food coloring. The procedure: begin by filling the plastic bottle almost full with vegetable oil. Add a few drops of food coloring to 1 tablespoon of water. And then add this to the plastic bottle's contents. You'll notice that the oil and water are not miscible, which is what will allow us to make bubbles within the oil. The water sinks to the bottom of the bottle, since it is more dense than the oil. Ground up an Alka-Seltzer, R, tablet and add the pieces/powder to the bottle, and then seal the cap. When the chemicals in the table dissolve and react, carbon dioxide gas bubbles will be formed, see equation below, which will lower the overall density of the water bubbles, allowing them to rise to the top of the bottle. When they reach the top, they will leave the water bubbles and join the small amount of air at the top of the bottle. At this point, the water bubbles will again be denser than the oil, so they will sink back to the bottom of the bottle. This process will repeat until all of the Alka-Seltzer, R, has been reacted. You should see colored bubbles move throughout the bottle, similar to a lava lamp.
What is absolute zero?
Lowest theoretical temperature, 0.00 K, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit.
What is absolute zero?
Lowest theoretical temperature, 0.00 K, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit.
What is absorption?
Capture of one material into another, can be a physical or chemical.
What is absorption?
Capture of one material into another, can be a physical or chemical.
What is process accuracy?
Closeness of a measurement to the actual or accepted value.
What is process accuracy?
Closeness of a measurement to the actual or accepted value.
What is an acid?
A molecule that has easily removable hydrogen ions, Brønsted-Lowry acid. Can accept a pair of electrons, Lewis, or releases hydrogen ions in solution, Arrhenius.
What is an acid?
A molecule that has easily removable hydrogen ions, Brønsted-Lowry acid. Can accept a pair of electrons, Lewis, or releases hydrogen ions in solution, Arrhenius.
What is an actactic polymer?
A polymer in which the chiral centers are arranged randomly along the chain.
What is an actactic polymer?
A polymer in which the chiral centers are arranged randomly along the chain.
What is the activation energy?
Difference in energy between the reactants and transition state. Or activated complete, for a chemical reaction or process.
What is the activation energy?
Difference in energy between the reactants and transition state. Or activated complete, for a chemical reaction or process.
What is an adiabatic?
A process that does not absorb or release energy.
What is an adiabatic?
A process that does not absorb or release energy.
What is adsorption?
Capture of one material onto the surface of another.
What is adsorption?
Capture of one material onto the surface of another.
What is an aerosol?
Suspension of a solid or a liquid in a gas, e.g., smoke, fog.
What is an aerosol?
Suspension of a solid or a liquid in a gas, e.g., smoke, fog.
What is an aliquot?
A sample taken from a larger amount of a material.
What is an aliquot?
A sample taken from a larger amount of a material.
What is an alkali?
A basic substance, i.e., pH 7.
What is an alkali?
A basic substance, i.e., pH 7.
What is an alkali metal?
Group 1 of the periodic table, i.e., Li, Na, K, Rb, Cs, Fr.
What is an alkali metal?
Group 1 of the periodic table, i.e., Li, Na, K, Rb, Cs, Fr.
How can I observe layers of immiscible liquids?
Chemistry principles encountered in this experiment: density, miscibility, polarity, materials. You'll need asterisk. Honey, pancake syrup, liquid, dish soap, water, vegetable or cooking oil, rubbing. Alcohol, lamp oil, a tall glass of water or other container, optional, food coloring to improve visibility asterisk note. For this experiment, it is not necessary to have every material listed. The procedure: pour the densest liquid into the glass first. Note: that the liquids above are listed from most dense to least dense. Try to avoid letting the liquid run down the sides of the glass. Gently pour the second liquid on top of the first. One way to pour it a little more slowly is to pour the liquid over another object such as a butter knife or the backside of a spoon. Allow each layer of liquid to settle for at least a few seconds before adding the next liquid. You'll notice that, instead of mixing, the liquids tend to stay in separate layers. The reason for this is that they are immiscible, which means that it is more thermodynamically favorable for the liquids to stay separated in layers and to form an interface than it is for them to mix together. Whether or not two liquids will be miscible is dictated by the details of the entropic and enthalpic factors associated with the mixing or separation of the two liquids in question. This is often directly related to whether or not the compounds have similar polarity. For example, we know water is a very polar substance, while vegetable oil is composed of primarily long, nonpolar hydrocarbon chains. These do not interact favorably with one another, and prefer to stay in separate layers. Continue pouring the third, fourth, etc. liquids on top of each other in order of decreasing density. You can just follow order of your liquids in the list above. As you pour in the successive liquids, they should continue to form separate layers. The densest liquids are affected the most by gravity, so these tend to stay below the less dense liquids. These liquids are not miscible, so they do not mix together to form a single solution. In truth, if you wait long enough, some of these liquids will mix together. But it will take a while. That's it. You should now see a series of separate liquid layers in your container.
How can I show my friends a magic trick using pepper?
Chemistry principles encountered in this experiment: polarity, surface tension, materials you'll need: a shaker or small packet of black pepper, dishwashing soap, a few drops, bowl water, a bowl full. The procedure: begin by filling the bowl with water. Then pour black pepper onto the water to form a thin layer of pepper across its surface. As a control experiment, try dipping your finger below the surface of the water. Nothing too interesting should happen at this time. Now rub a small amount of dishwashing soap on your finger and dip it in the water again. This time, you should see the pepper move away from your finger and toward the edges of the bowl. The nonpolar soap molecules don't want to dissolve beneath the surface of the water, and thus they spread across the surface of the water quickly, which lowers its surface tension. Whereas water typically bulges a bit above its surface due to its relatively high surface tension. The water spreads out when its surface tension is lowered. This causes the water to spread out as the soap moves over it, and the pepper is carried away from your finger in the process. Now that you understand the basics of this trick, you can perform it for your friends. Ask a friend to dip their finger in the water and to try to Concentrate on trying to make the pepper move away from their finger. When they cannot make it happen, you can step in and use your already soapy finger to easily move the pepper away.
What is absorption?
Capture of one material into another, can be a physical or chemical.
What is adsorption?
Capture of one material onto the surface of another.
How can I make a volcano from vinegar and baking soda?
Chemistry principles encountered in this experiment, chemical reactions, gases, materials you'll need. Vinegar, baking soda, 2 tablespoons, large bowl, baking pan flour, 6 cups, cooking oil, 4 tablespoons. Salt, 2 cups, plastic bottle, dishwashing soap, red or orange food coloring, or any color, really. Water. The procedure. This is a classic chemistry experiment that you might have done before in school. In a large bowl, first mix 6 cups of flour, 2 cups of salt, 4 tablespoons of cooking oil, and 2 cups of water. Mix these ingredients until they are firm. These ingredients are not involved in the chemical reaction that will make your volcano erupt, but rather this mixture will serve as the rock that forms the structure of your volcano. Place the plastic bottle standing vertically in the pan. Use your hands to shape the rock material from the first step into a cone shape around the top of the bottle. Be careful not to cover the top of the bottle. Fill the bottle most of the way with water, leaving enough space to add a few ounces of baking soda and vinegar. Add a few drops of dishwashing soap to the bottle. This is not part of the chemical reaction that will take place inside the bottle, but bubbles from the soap will help to catch the gas evolved during the reaction between the vinegar and baking soda. Add 2 tablespoons of baking soda into the bottle. Finally, slowly or quickly, if you want a really crazy volcano, add vinegar to the bottle, and prepare to witness the eruption. Be careful though, you should avoid getting this mixture in your eyes or anyone else's, and this combination can make a spectacular mess in your kitchen. The chemical reaction takes place between the baking soda, sodium bicarbonate, or NaHCO3, and vinegar. Dilute acetic acid, or CH3CO2H, to release carbon dioxide gas, which is what causes the volcano to erupt. The relevant chemical equation is NaHCO3 plus CH3COOH CH3COO Na and CO2 plus H2O.
What is an adiabatic?
a process that does not absorb or release energy.
What is an acid?
A molecule that has easily removable hydrogen ions, Brønsted-Lowry acid. Can accept a pair of electrons, Lewis, or releases hydrogen ions in solution, Arrhenius.
Do you notice a change in the part that you dipped into the solution?
Place the remaining pennies into the solution. You will likely notice a visible reaction as the pennies are placed in the solution. The reason pennies eventually begin to appear dull is that the copper surface reacts with oxygen in the air to create a layer of copper oxide. In this experiment, the vinegar and salt will react with the copper oxide and remove it, which will leave a layer of the original shiny copper exposed on the surface. Allow the pennies to remain in the solution for several minutes. If necessary, try to move the coins around so as to expose both sides of each coin to the solution. If possible, flip the coins over after a couple of minutes. Drain the solution and rinse the coins with clean water. They should now look clean and shiny.
What is the Maillard reaction?
The Maillard reaction is technically non-enzymatic browning, which basically includes any kind of browning that happens when you're cooking, but excludes what happens to cut apples you leave out on the counter. At the chemical level, it's a reaction between an amino acid and a sugar in the presence of heat. A huge number of chemicals are formed in these processes, so you can't really pin down the Maillard reaction to a single set of chemical steps. These processes are responsible for the browning of meat, the malting of barley for beer, the roasting of coffee, and the browning of the crust of bread.
What is process accuracy?
Closeness of a measurement to the actual or accepted value.
Is caramelization the same thing as the Maillard reaction?
Caramelization is the breakdown of sugar molecules with heat. Pyrolysis, while the Maillard reaction requires amino acids, proteins. Caramelization, like the Maillard reaction, is a term for hundreds of different chemical reactions taking place at the same time.
How can I observe the effects of electrostatic forces using household objects?
Chemistry principles encountered in this experiment: electric charge, electrostatic forces, materials you'll need: nylon hair comb, or a latex balloon, a water faucet. The procedure: comb your hair with a nylon comb. If you don't have a comb, you can also rub your head with an inflated latex balloon instead. As you rub the comb or balloon to your head, it builds up an electric charge on the object due to the movement of electrons between the object and your head. Go to the faucet and turn it on so that a narrow stream of water flows out. Try to make the stream as thin as possible, while still maintaining a steady, smooth flow of water. With the water running, move the comb or balloon close to the stream of water. But be careful not to actually let the comb or balloon touch the water. As it gets close, the stream of water should be deflected toward the comb or balloon. This is because the charge in the object, comb or balloon, induces an opposite charge in the nearby water. And the object and water then experience an attractive electrostatic interaction: opposites attract. You can experiment with how the amount of deflection varies with the size of the stream of water from the faucet. You can also compare the ability of various objects, different combs, balloons, or different objects altogether, or vary the amount of time you rub the object in your hair.
How can I make black snake fireworks from items around my house?
Note: this experiment involves fire and flammable materials, so adult supervision is required. Also, check your local laws before attempting this experiment. Chemistry principles encountered in this experiment: chemical reactions, combustion reactions, materials you'll need: sand, about 2 cups, lighter fluid, a small bottle of about 100 milliliters. Baking soda, 1 tablespoon, sugar, 4 tablespoons. Cup or bowl: an outdoor location where you can light the black snake firework safely without damaging anything. The procedure: in a cup or bowl, mix 4 tablespoons of sugar with 1 tablespoon of baking soda. Use the sand to form a pile, in your chosen safe outdoor location. And then create a depression in the middle of the sand. This depression is where you will ignite the black snake firework. Pour a small amount of lighter fluid onto the sand to wet it. Try this experiment first with a very small amount of lighter fluid, and, if necessary, repeat the experiment with incrementally larger amounts. It's better to start too small than too big. Pour your mixture of sugar and baking soda into the wetted depression in the sand. You don't have to use it all at once. Feel free to experiment with different quantities of the baking soda and sugar mixture. Carefully ignite the lighter fluid with a match and stand back. You should see the mixture create long snakes of black ash. The burning sugar and baking soda form sodium carbonate, water vapor, and carbon dioxide gas. The ash in the snake is composed of carbonate and burnt carbon.
If baking soda and baking powder are different, how can I substitute one for another?
Since baking powder is diluted baking soda with acid. If your recipe calls for powder but you only have soda, you'll need to use less, but add an acid. Generally the ratio is 3 parts baking powder equals 1 part baking soda with 2 parts cream of tartar, or another acid substitute.
How can I study the effects of acids and bases on sliced fruit getting old and turning brown?
Chemistry principles encountered in this experiment: acids and bases, biochemical/enzymatic reactions, materials you'll need: an apple. Other fruits like bananas, pears, or peaches will also work. 5 clear plastic cups vinegar, lemon juice, baking soda, water, milk of magnesia, measuring cups. The procedure: prepare aqueous solutions of milk of magnesia and baking soda. The amount of water you use isn't particularly important. Feel free to test various concentrations if you'd like. The key aspects are that the baking soda dissolves completely and that the milk of magnesia solution becomes less viscous or thick. Slice your apple, or other fruit of choice, into 5 pieces. If you have decided to test multiple concentrations of baking soda or milk of magnesia solutions, adjust the number of fruit slices accordingly. Label the cups as follows: vinegar, lemon juice, baking soda solution, milk of magnesia solution, and pure water. Place 1 slice of fruit in each cup. Add about degree of a cup of the appropriate solution to each of the cups you have labeled. The fruit should not be completely submerged in the solutions, but make sure each slice of fruit gets completely coated with the solution. The vinegar and lemon juice solutions serve as acidic solutions, of acetic and citric acids, respectively. The baking soda and milk of magnesia solutions serve as basic solutions of sodium bicarbonate and magnesium hydroxide, respectively, while the water serves as a neutral control solution. Write down your observations regarding the physical appearance of each piece of fruit at this time. If you have a camera handy, it might be useful to take a picture of your fruit samples for comparison to the final results. Allow the fruit to sit for 1 day, and then come back and record your observations again. If you took a picture on the first day, you can compare the current appearance of the fruits to your photograph. Apples and fruits turn brown when an enzyme called tyrosinase, refer back to chemistry in the kitchen, carries out a chemical reaction in the presence of oxygen and phenol-containing compounds.
What is an aerosol?
Suspension of a solid or a liquid in a gas, e.g., smoke, fog.
What is radio astronomy?
Radio astronomers study what's going on in outer space by using radio waves. As opposed to telescopes, which use light in the visible region of the spectrum. This approach has some distinct advantages, perhaps the most obvious being that radio astronomers can work at any time of the day, while astronomers who rely on light telescopes can only work at night. Radio astronomy relies on monitoring weak radio wave signals coming in from outer space, and knowing how to interpret these signals to draw conclusions about the locations of celestial bodies and events that have taken place far, far away.
What's in Jello, that makes it so jiggly?
Gelatin, which is a convenient and pleasant term for the mixture of proteins and shorter peptides that are obtained from boiling byproducts of the meat and leather industries. Mostly bones and pig skin, makes Jello, jiggly. The hydrogen bonds between peptide strands allows gelatin to form a network in the presence of water, which is what the physical structure of the gel is that you are familiar with. These hydrogen bonds can be disrupted with heat, which is why you boil Jello, before pouring it into a mold. Once it cools back down, the network reforms in whatever shape the liquid is in.
What is the activation energy?
Difference in energy between the reactants and transition state, or activated complete, for a chemical reaction or process.
How can I use chemistry to make dull pennies shiny?
Chemistry principles encountered in this experiment: surface chemistry, oxidation reactions, materials you'll need. A handful of dull pennies, 10 will do, 1 teaspoon table salt, sodium chloride. 1/4 cup white vinegar, acetic acid solution, a small, non-metallic bowl, water, paper towels or napkins. The procedure: pour 1/4 of a cup of vinegar and 1 teaspoon of table salt into the bowl. Stir the mixture until the salt is completely dissolved. Try first dipping 1 penny into the solution for about 15 seconds and remove it.
How can I make hot ice, sodium acetate?
Chemistry principles encountered in this experiment: chemical reactions, solubility, crystallization and recrystallization, colligative properties. Materials you'll need: pan with cover, microwave or stovetop, vinegar, 1 liter, baking soda, 4 tablespoons, dish. The procedure: pour the vinegar into a pan, and very slowly, a little bit at a time, add the baking soda. As you may already know, this reaction will produce large amounts of bubbles. Carbon dioxide gas, so you'll need to add this very slowly. This reaction will produce a solution of sodium acetate in water. Sodium acetate is produced according to the chemical equation Na plus HCO3 plus CH3COOH CH3 Co Na plus H2O and CO2. Bring the solution to a boil. Allow the solution to continue to boil until a skin or film begins to form on the surface of the solution. This will require heating for a significant amount of time, perhaps up to an hour, until a large fraction of the water from the vinegar has evaporated. Our goal here is to form a very concentrated hot solution of sodium acetate. You'll recall from our discussion of colligative properties that the solubility of a solute is higher at higher temperatures. As we reduce the volume of the water, the sodium acetate will not evaporate, and we will be left with a concentrated solution at high temperature. When you notice a film start to form on the surface, remove the pan from the heat, and cover it to prevent further evaporation. Place it on the countertop or in the refrigerator to cool. If you see any crystals begin to form, add a small amount of additional vinegar, or if you are out of vinegar, use water and stir the solution so that they dissolve. You now have a supercooled solution of sodium acetate that can crystallize out of solution readily if a crystallization nucleus is present. You can now slowly pour the first few drops of the cooled solution onto a dish, and it should begin to crystallize rapidly. If it doesn't, try dragging a fork or knife along the dish to make a tiny scratch. Or give the liquid a moment to evaporate a little so that the sodium acetate begins to crystallize before you begin to pour. As you continue to pour, the liquid should continue to crystallize as it contacts the crystals already formed on the dish. This is similar in spirit to how purification takes place during a recrystallization. See the modern chemical lab. If you feel the crystals, they will be warm to the touch. Since the crystallization is an exothermic process, it gives off heat. This is why it's called hot ice. But now you know it isn't really ice, it's sodium acetate, and you know how to make it.
What is cream of tartar?
Cream of tartar is the potassium acid salt of tartaric acid. This means one acidic hydrogen of tartaric acid is replaced with a potassium ion. The structure is shown below. If you've ever seen crystals of something in a bottle of wine, or even fresh grape juice, it was probably this chemical.
How can I make slime?
Chemistry principles encountered in this experiment. Hydrogen bonding synthesis, polymer chemistry, cross-linking materials. You'll need water, Elmer's glue, about 4 ounces. or 120 ml, borax powder, 4 to 5 tablespoons, bowl measuring cup small jar. Doesn't need to have a cover, spoon or stirring device. Food coloring, optional. The procedure. Pour about 4 ounces of white glue into the jar. The glue contains several components, including the polymers polyvinyl acetate and polyvinyl alcohol. See polymer chemistry. Polyvinyl acetate contains oxygen atoms that can serve as hydrogen bond acceptors, and polyvinyl alcohol contains hydroxyl groups that can serve as either hydrogen bond donors or acceptors. Add 1/2 cup, 4 ounces or 120 ml, of water, and stir it in until it mixes with the glue. Note that there is already some water in the glue, and we are just adding more. Optional, add food coloring to the mixture to give your slime some color. In the bowl, mix 1 cup, 8 ounces or 240 ml, of water with 4 or 5 tablespoons of the borax powder. Stir this well. Here we are preparing a solution of borax so that we can add it to the mixture of glue and water in a more uniform fashion. While mixing, slowly add the glue and water mixture to the solution of borax. As you mix, you should observe the slime forming. Pick it up with your hands and knead it until it seems fairly dry. There will still be extra water left behind in the bowl, that's nothing to worry about. The borax serves to cross-link the polymers by forming hydrogen bonds with the oxygen atoms of the polymers in the glue. These interactions can readily rearrange to form new hydrogen bond donor acceptor pairs with different oxygen and hydrogen atoms, which is what makes the glue so stretchy and readily deformed. When you are done with it, you can store the slime in a plastic bag in the refrigerator.
How does baking soda make my cookies better?
Baking soda is sodium bicarbonate, NaHCO3, and is used in cooking as a leavening agent, as in, it helps things to rise. It does this by releasing carbon dioxide, CO2, which it does in the presence of acids like buttermilk, vinegar, lemon juice, cream of tartar, and so on. The process is much faster at higher temperatures. Once you put your cookies in the oven, the sodium bicarbonate begins to break down, and the carbon dioxide that is released makes tiny little bubbles in the batter. These tiny bubbles get trapped as the cookies bake, making them light and fluffy.
What is an aliquot?
A sample taken from a larger amount of a material.
What is an alkali metal?
Group 1 of the periodic table, i.e., Li, Na, K, Rb, Cs, Fr.
What is an alkali?
A basic substance, i.e., pH 7.
Do chemists really study food chemistry?
Yes, they really do. There's even a scientific journal called Food Chemistry, published by Elsevier, dedicated to reporting new findings regarding the chemistry and biochemistry of food and raw food materials.
What is absolute zero?
Lowest theoretical temperature, 0.00 K, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit.
How can I make invisible ink?
Chemistry principles encountered in this experiment. Evaporation combustion reactions acid/base reactions materials you'll need, cotton swab or paintbrush heat source. Can be a light bulb, measuring cup paper baking soda water grape juice, optional, the procedure. To prepare the ink, just mix equal volumes of water and baking soda and stir well. Take a cotton swab, paintbrush, toothpick, or something similar, and write a message on a piece of white paper using the water and baking soda mixture you have prepared. Allow the ink time to dry. The water will soak into the paper and eventually evaporate. But the baking soda will not evaporate and it will be left behind. To read your invisible message there are a couple of options. One is that you can hold the paper to a heat source, such as a light bulb or gentle flame. Don't burn the paper. This should cause the baking soda on the paper to turn brown, revealing your message. The baking soda burns faster than the paper, which is why it turns brown before the paper does. Another option is to spread purple grape juice over the paper. You can use a paintbrush to do this. The message should appear in a different color/shade compared to the rest of the paper. This works because an acid in the grape juice reacts with the sodium bicarbonate that you used to write your message.
What chemicals are used to preserve food?
There are two main types of food preservatives: those that prevent oxidation and those that prevent bacteria or fungi from growing. The first are appropriately named antioxidants, and these molecules work by reacting with oxygen themselves. Unsaturated fats are common targets of oxygen, which causes foods to become rancid. Antioxidants provide an even easier target for oxygen to attack. preventing O2 from wreaking havoc in other ways. Natural antioxidants include molecules like ascorbic acid, vitamin C. And there are also many unnatural antioxidants on the market. The second class of preservatives are those that stop the growth of bacteria and fungi, like mold, from growing. Many of these preservatives are acidic molecules that can be absorbed into the cells of bacteria. If enough acid gets into the cell, basic biochemical functions, specifically fermentation of glucose, slow down enough that the cell dies, and your food stays fresh.
How can I test the hardness of objects around my house?
Chemistry principles encountered in this experiment: hardness materials, science materials you'll need. Collect several materials of known hardness. Examples include, numbers are based on the Mohs scale. Fingernail, 2.5, penny, 3, glass, typically 5.5 to 6.5, quartz, 7, steel, typically 6.5 to 7.5, sapphire. 9. You can also look for additional items from the list provided at the end of this experiment. Or search online for additional objects that have been ranked on Mohs scale of hardness. Of course, you can also choose item of unknown hardness and determine their hardness in this experiment. The procedure: locate a specimen whose hardness you want to test. Note that you will be attempting to scratch the object. So don't choose anything too valuable or anything you don't want scratched. Select an object of known hardness from those you gathered, and try to scratch the surface of your sample by pressing it with the tip or edge of the object of known hardness. For example, let's say you wanted to test a piece of wood. You could try to scratch it with a piece of quartz by pressing the edge of the quartz into the wood. Inspect your sample to see if you have made a scratch in it. You may need to feel the surface of the object with your finger to check thoroughly. If your object was softer than the sample of known hardness, there will be a scratch. If it was harder, then there will not be a scratch. Repeat the test a couple of times to verify the result. Continue performing the scratch test with various objects of known hardness, until you find two adjacent objects on your list, such as a fingernail, 2.5, and a penny, 3, in between which the hardness of your sample rests. You will know you've found this pair of objects on your list when the harder object of the pair does scratch your sample, while the softer one does not. Once you have found this place on the list, you can assert that the hardness of your unknown must lie between that of the two objects of known hardness on the list. For example, if a penny, 3, scratches your object, and a fingernail, 2.5, does not, your object must have a hardness between 2.5 and 3. Additional Mohs hardness rankings: talc, 1, gypsum, 2, calcite, 3, fluorite, 4, platinum or iron, 4.5, apatite, 5, orthoclase, 6, quartz, 7, garnet, 7. Hardened steel, topaz, emerald, 8, corundum, 9, diamond, 10.
How does pectin gel make jelly?
Pectin is a polysaccharide from the cell walls of plants that helps plant cells to grow and also to stick to their neighbors. Commercially, pectin is extracted mostly from citrus peels, but other plants are also used. Pectin is the gelling agent that helps jams and jellies to set, giving them a consistency that is useful for spreading on toast. It does this using a very similar mechanism as the one it uses to keep plant cells together. The chains of sugar molecules, polysaccharides, can form bond between strands, creating an elastic network known as a gel, or jelly.
What is a superbubble?
A superbubble is a cloud of superheated gas that can be formed when multiple stars that are relatively near each other die out at similar times. This situation can lead to an explosion that spans hundreds of light years in distance. Recall that a light year is the distance that light travels through space in a year. So we are talking about an absolutely huge explosion. The light generated from this explosion is often not in the visible range of the spectrum, so they can't always be seen by the naked eye, not to mention the fact that they are also very, very far away.
What is an actactic polymer?
A polymer in which the chiral centers are arranged randomly along the chain.
What's the difference between baking soda and baking powder?
Baking powder is a mixture of three things: baking soda, an acid, and a filler, usually cornstarch. The acid takes the place of the buttermilk or lemon juice in a recipe, see the previous question. To release CO2 from NaHCO3. The starch is in the mix to keep the two components from reacting before it gets into your cookies and to keep everything dry.
What is an alkali earth metal?
Group 2 of the periodic table, i.e. B, Mg, Ca, Senior, Ba, Ra.
What is an alkali earth metal?
Group 2 of the periodic table, i.e. B, Mg, Ca, Senior, Ba, Ra.
What is an allotrope?
Different arrangements of atoms of a single element, e.g., diamond and graphite are allotropes of carbon.
What is an allotrope?
Different arrangements of atoms of a single element, e.g., diamond and graphite are allotropes of carbon.
What is an alloy?
A mixture of metals, e.g., bronze, a mixture of zinc and copper.
What is an alloy?
A mixture of metals, e.g., bronze, a mixture of zinc and copper.
What is an alpha particle?
A particle consisting of 2 neutrons and 2 protons, i.e., a helium nucleus.
What is an alpha particle?
A particle consisting of 2 neutrons and 2 protons, i.e., a helium nucleus.
What is an amalgam?
An alloy of mercury.
What is an amalgam?
An alloy of mercury.
What is amorphous?
A solid without a repeating, ordered structure.
What is amorphous?
A solid without a repeating, ordered structure.
What is an amplitude?
The height, or maximum displacement, of a wave.
What is an amplitude?
The height, or maximum displacement, of a wave.
What is an angstrom?
A unit of length used often to describe bond lengths. 1A equals 10 to 10 m.
What is an angstrom?
A unit of length used often to describe bond lengths. 1A equals 10 to 10 m.
What is anhydrous?
Without water.
What is anhydrous?
Without water.
What is an anion?
A negatively charged ion.
What is an anion?
A negatively charged ion.
What is an anode?
The electrode at which oxidation occurs.
What is an anode?
The electrode at which oxidation occurs.
What is the antibonding orbital?
Orbitals in which the component atomic orbitals are out of phase, leading to repulsion or destabilization.
What is the antibonding orbital?
Orbitals in which the component atomic orbitals are out of phase, leading to repulsion or destabilization.
How can I make a cloud form in a bottle?
Note, this experiment involves fire and flammable materials. Adult supervision is a must. Chemistry principles encountered in this experiment: ideal gas law, phase changes, droplet formation, materials you'll need. 20-ounce or 1-liter plastic soda bottle, warm water, 1 to 2 ounces. Matches the procedure. Add warm water to the soda bottle until the bottom is just barely covered with water. With the bottle tip so that you don't burn yourself. Ignite a match and insert the burning end of the match into the bottle. Allow the bottle to fill up with smoke. When the bottle is fairly filled with smoke, or when the match goes out, Remove the match and screw the cap on to close the bottle. Clouds will form when water vapor forms small but visible droplets around particles in the air. In this experiment, the smoke will provide these particles around which the water can form small droplets. With the bottle closed, squeeze it several times. You should see a cloud form when you squeeze the bottle. The temperature of the gas inside may temporarily increase, but the temperature will quickly equilibrate with the surroundings. Recall the ideal gas law we discussed in Atoms and Molecules, PV equals NKBT. When you release the squeezed bottle, the temperature inside decreases, cooling the water vapor and helping it to liquefy into droplets on the particles provided by the smoke. This is very similar to how real clouds are formed in the atmosphere.
What is an alpha particle?
A particle consisting of 2 neutrons and 2 protons, i.e., a helium nucleus.
What is splenda, R?
Splenda, R, is a commercial name for an artificial sweetener, like NutraSweet, R, or Equal, R. Sucralose is the key sweet ingredient in Splenda, R, but unlike natural sugar molecules, sucralose is not metabolized, so it effectively has 0 calories. It's made from regular table sugar by selectively exchanging 3 O groups for chlorine atoms.
So is there any real way to stop onions from making you cry?
Everyone's mother seems to have their own unique proposal about how to avoid crying over diced onions. But there's only one that makes any chemical sense. Excluding wearing a gas mask, put the onion in the fridge before you cut it. Almost every chemical reaction is slower at lower temperature. And since the lacrimator in onions is produced when you cut it, and not naturally present in the onion, you can give yourself more tear-free time to dice if the onion is cold.
How can I make a lava lamp at home?
Note, okay, so we'll disclose up front that this experiment won't actually make a lamp. It will make a device with bubbles that rise and fall just like a lava lamp. But you'll need a flashlight or other light source if you want it to be illuminated. Chemistry principles encountered in this experiment: chemical reactions, density, miscibility, gases, materials you'll need. Vegetable oil, 20 ounces. Plastic soda bottle, 20 ounces or 1 liter, water, 1 tablespoon. Alka-Seltzer, R, food coloring. The procedure: begin by filling the plastic bottle almost full with vegetable oil. Add a few drops of food coloring to 1 tablespoon of water. And then add this to the plastic bottle's contents. You'll notice that the oil and water are not miscible, which is what will allow us to make bubbles within the oil. The water sinks to the bottom of the bottle, since it is more dense than the oil. Ground up an Alka-Seltzer, R, tablet and add the pieces/powder to the bottle, and then seal the cap. When the chemicals in the table dissolve and react, carbon dioxide gas bubbles will be formed, see equation below, which will lower the overall density of the water bubbles, allowing them to rise to the top of the bottle. When they reach the top, they will leave the water bubbles and join the small amount of air at the top of the bottle. At this point, the water bubbles will again be denser than the oil, so they will sink back to the bottom of the bottle. This process will repeat until all of the Alka-Seltzer, R, has been reacted. You should see colored bubbles move throughout the bottle, similar to a lava lamp.